So our next speaker is going to be Mitesh Khapra. He is an assistant professor in the Department of Computer Science and Engineering at IIT Madras. So he works in the areas of deep learning, multilingual, multimodal, multilingual processing. And he's also worked as a researcher at IBM Research India. He's worked on several interesting problems while at IBM Research, including statistical machine translation, cross-language learning, multimodal learning, and completed his PhD in MTech from IIT Bombay. And his PhD thesis was on a very important problem of reusing resources for multilingual computation. And he is also a recipient of the Google Faculty Research Award in the year 2018. Yes, all yours, Mitesh.
So, hi, I'm going to talk about object detection over scientific plots. This is work done primarily by my students, Preeta and Nitesh. And Pratyush and I have advised them on this project. The slides are prepared by Preeta. I'm presenting on her behalf. So let's start with the introduction. So today, wherever you are, it's very easy to find a lot of plots around you, whether you are reading a journal article or newspaper articles or scientific articles, financial reports, right? Especially in the COVID world, I don't think a single day goes by without us looking at the plots of mortality rates, recovery rates, active cases, and so on, right? So now, given that there's so much plots around us, the problem statement or the research problem that we are interested in is fast and accurate detection of elements in scientific plots. So what do I mean by that? This is what I mean by that. So here you have a bar graph, a line plot, a dot line plot, or a dot plot, and you want to detect all the visual and textual elements in this scientific plots. So the visual elements are, of course, the bars, the legend markers, and the dots and the squares that you see. And the textual elements are various titles of x-axis titles, y-axis titles, the plot titles, and also the legend names, etc. Right? Now, why would you want to do this? Right? Why would you want to detect all the visual elements in a plot? Because this is useful in various downstream applications. For example, if you have a plot, you would want to construct a table with the data that the plot is representing. And once you have this table, you could have several question answering problems on top of that, right? For example, you could ask the question, what is the average number of neonatal deaths in Cuba across years? And you could answer it from this table. But that's fine. Why do you still need to detect elements in the plot? This is about question answering over tables. Because to construct this table, you'll have to detect the corresponding elements from the plot. You'll have to see that there is a x-axis title, which is years. So years would be one column in your table. Then there are different years. So the year 2004 would be one of the rows in your table. Then there are different countries which are being compared. So there would be one column for Bulgaria, one column for Cuba. And then across different of all these combinations, you would have to read the values of these bars, right? For example, the cyan bar, which I have highlighted for the year 2003, it has a value somewhere between 500 and 600. And I need to be able to calculate that. To be able to do this, I need to detect all the plot elements, including the x-axis, y-axis, titles, tick labels, and the bars, the exact boundaries of the bars, right? So this is why object detection over plots is important. Now, So the question now is, are existing object detection models good enough for this task? Just give me a minute. Sorry, my daughter just walked in, so I have to take care of that. Yeah, so the question now is that if this is really an important problem, object detection has been around for quite some while. So aren't the current models good enough for this task? So let's see whether this task is similar to object detection over natural images, which is the more popular topic which has been around for many years. Right? So this is what a natural image looks like, and I've deliberately blurred it because I want to show certain boxes on top of it. So natural image is one which you see in typically in a scenic environment, and you have a single object at the center or a few objects in the image, right? And these objects are typically big in size. And if I compare this with a scientific plot, this is what a scientific plot looks like, right? So the first difference, of course, is that in a natural image, you only have visual elements, right? So you just don't have any text here. Whereas if you compare it with a scientific plot, you have visual elements, but in addition, you also have textual elements, right? So you have these different 2002, 200, 300, and even the titles and so on, right? So you have both visual as well as textual elements, where the natural images, you only have one type of object. The second difference is, if you look at the sizes and the aspect ratios of the objects, then in a natural image, you will find small, medium, and large objects, whereas in a scientific plot, the range is a slightly wider than that. You will have very small objects like the zero here, which I have highlighted, and you could have very long objects like the titles of the x-axis or y-axis or the plot. And also the aspect ratios are a bit different in scientific plots, right? So you could have a very thin but a very long bar. You could have a very wide but thin title, and so on, right? So there's quite a bit of variation in the sizes and the aspect ratios of the objects that you deal with in scientific plots. The third thing is the importance of structural relationships. So in a scientific plot, so if you have the legend marker, which I've highlighted in red here, then you know that near it somewhere there should be a legend name. And this information of the neighboring objects is useful in detecting new objects in the plot. Of course, such relations also exist in natural images. For example, if you see a sofa, then maybe there's a cat sitting on it. If you see a dining table, then maybe there are people around it eating food. But I'm just saying that these relations are more prevalent in scientific plots, where almost everything has a neighboring element which should exist for this element to exist. For a bar to exist, the corresponding tick label on the x-axis should be there, and so on, right? So these structural relationships could be better exploited. And lastly, the evaluation itself, right? So if you look at natural images, now here I'm trying to detect a cat. The actual annotator has, human annotator, has marked the cyan box as the true box, right? So this is the box according to a human annotator which contains the cat. Now, one algorithm which we tried has predicted the red box as the box in which the cat is contained. Now, is this prediction correct or incorrect? How do you determine that? It would be very harsh to say that I will mark a prediction as correct only if it exactly matches the cyan box that a human has marked. For example, in this case, even if I treat this red box as a prediction, it's fairly accurate. 95% of the cat is inside the box. And in most practical applications, I would be okay with such kind of a prediction, right? Therefore, when you're doing object detection over natural images, you compute the precision by using the following definition. You compute the intersection over union between the true box and the predicted box. What does that mean? It roughly means the overlap between the true box and the predicted box. And if this overlap is higher than 50%, then you say that, okay, your prediction is correct. But if I were to use the same metric for object detection in scientific plots, then I have a red box detected here, which has a greater than 50%. It's actually around close to 75% overlap with the true box, right? But if I were to mark this as correct, I would be in trouble, because in downstream applications, the value of this red bar would be read as something around 580, whereas the actual value was around 630. Now, if I read the value of this bar as incorrect, then all my downstream question answering, table generation, everything would suffer. So in the case of scientific plots, you need much stricter evaluation matrix. In particular, an overlap of 0.5 is not acceptable. You need to evaluate at much stricter overlaps, at least of 90%, right? So something like this is acceptable, where the true box has a 90% overlap with the predicted box. So clearly there are additional challenges in object detection over scientific plots, but just listing down these challenges isn't enough to convince you that existing methods for object detection over natural images are not sufficient for this problem, right? Hence, the first goal of this work, and that's perhaps the only goal that I'll be able to cover in the time that I have, is to investigate whether existing object detection methods are adequate for detecting text and visual elements in scientific plots, which are different than the objects found in natural images, right? So the goal is take a scientific plot, take an army of object detection networks out there. So in particular, we have taken 6 state-of-the-art object detection networks, and they're grouped into 2 classes. One class is what is known as 2-stage detectors, and I'll shortly tell you what that means. And the other class is 1-stage detectors. Again, I'll tell you what that means. And we want to see that whether these methods are capable of accurately detecting objects in scientific plots, right? So let's start with a quick summary of 2-stage detectors. So what does a 2-stage detector do? You take an image, Then you propose a large number of regions on this image. So you say that here are all these rectangles on this image, and I think there are certain objects inside these images. How do you do that? You could just do a brute force approach where you say that I am going to create rectangles of size 10 cross 15, and I'm going to slide it throughout the image. Starting from here, I'm going to slide it throughout the image. And for every such box, I'm going to ask the question whether it contains an object, and if it contains the object, what is the type of the object? Is it a horse? Is it a person? Is it a car? Is it a bicycle? So that becomes a classification problem. And at the same time, since I'm constructing arbitrary boxes, I also want you to stretch the box so that it actually corresponds with the object, right? So here, for example, this is a slightly smaller box than what the actual horse occupies. So I also want you to solve the regression problem where I need you to predict the width, height, and the leftmost corner of this box, right? So for every region proposal, I want to solve two problems. One is a classification problem to identify the type of object in the image, and the other is a regression problem to identify the coordinates of the rectangular box which contains the object, right? And the key thing here is that I have a separate stage which generates these region proposals, right? So that's something outside that I'm doing. I'm proposing a lot of regions. Here, for the sake of convenience, I have shown only 3 regions. Now, how do you go from here to the output? You essentially use deep learning. So you take this image, the cropped rectangular box, you pass it through a convolutional neural network, and then you construct some images for this feature, some feature representations for this input. And using those feature representations, you perform the classification and the regression task. And then you repeat the same for all the regions that you had identified or proposed. So let's take a minute here to make a few observations. So one is, this looks like a very expensive proposition, because for every region that I propose, I need to do this expensive computation of extracting the features and then doing the classification and regression. And also have a separate stage where I could actually propose a large number of proposals, right? So typically people propose of the order of 2,000 or 3,000 proposals on the image. And for all those proposals, I need to repeat this process. So this was the first object detection method that was proposed or deep object detection method that was proposed for this task. And since then, there have been several improvements focusing on the efficiency, right? So they have made improvements where now you can reduce the number of computations required in the network, as well as reduce the number of proposals that you generate, and also improve the quality of the initial proposals that you have generated, right? So this is the advancement that has happened in the past 6 years around efficiency, accuracy, and generating better proposals, right? And if I were to summarize the key contributions that have been seen in this space, then you have this model known as Fast RCNN, which proposed the ROI pool method, right? So what is ROI pool? So I have the box for the horse here, and then I have certain features extracted using a convolutional neural network. And now once I pass it to the classifier, I want that feature representation to be a fixed size. Why is that? There are 2 reasons for that. One is, if I have a horse as a region, and if I have the person as a region, both of these are originally of different sizes. This is rectangular, this is more squarish, and hence the feature representations of these would also have different sizes. One would correspond to a roughly rectangular shape, and the other would correspond to a square shape, right? But the classification network that I have, I should pass it inputs of the same size. Why is that? Because it's a deep neural network, and a deep neural network basically involves matrix multiplications. And we know that for matrix multiplications, the sizes of the matrices should be compatible. So I can't really multiply a 1 cross 3 matrix with a 5 cross 5 matrix. I can only multiply a 1 cross 5 matrix with a 5 cross 5 matrix. So what that means is that irrespective of what the original size is, the features that I generate should be of the same size, and they should be compatible with the rest of the network. Hence, they came up with a method which takes any input and maps it to a fixed size representation, and that involves certain approximation, right? So what this figure here is trying to show is that if you had this as the feature representation, you're going to do some trimming to just get the fixed size representation from that original feature representation. So that would obviously be a lossy process. So this was the idea which was originally proposed in Fast RCNN. Then the other idea was to generate region proposals efficiently. I'll not go into the details of this. So instead of using a brute force method which generates a lot of region proposals, this model, which is faster RCNN, came up with something known as a region proposal network, which efficiently generates regions and is also trainable. Hence, it generates more accurate regions in the image. And the last important idea was in mask RCNN, where they replaced the ROI pooling with something known as ROI align. So what it does, the key difference here is that, as you notice, this was a lossy process. ROI pool had some lossy approximation of the input features, but they came up with a less lossy process, which accounts for all the input features more efficiently while converting it to a fixed size representation. So there is less loss in this approach as compared to the original approach. And it has been shown that because of this lesser lossy approximation, this kind of pooling, this kind of alignment is better than the original method that was proposed in fast RCNN, right? So these are some of the key ideas that have been proposed in two-stage detectors. Right? Now, let's look at the counterpart, which is one-stage detectors. So in a one-stage detectors, the idea is to not propose any regions on the original image. Instead, just say that I'm going to think of the original image as a 7x7 or an n×n grid. And for every cell in this grid, I'm going to make the following decisions. I'm going to ask whether with high confidence, C here stands for confidence, what is the confidence that this grid or this cell actually lies at the center of an object. So for this particular cell, that confidence would be high because it actually lies at the center of this person object. At the same time, if it lies at the center of a person object, I'm interested in knowing the XY coordinates and the width and height of that object, right? So I'm interested in knowing that, suppose this is the XY coordinate, this is the height, and this is the width. So I'm interested in predicting all these quantities, right? So I'm interested in knowing whether this cell lies at the center of an object. If so, what is the coordinates of that object and what are the width and height of that object? Once I have done that, I also want to know what does that object look like? Is it a person? Is it a horse? Is it a cycle or a car, right? So if there are K classes, then in all, I'm going to make K predictions for the K classes, 4 predictions for the coordinates as well as the width and height, and 1 prediction for the confidence whether this box contains an object or not, right? So this is how they do it. They just make this decision for all the 49 cells in the input image without actually proposing any regions explicitly. And they do this for all the cells that you have. So this is for the first cell, and then they do it for another cell, and they keep repeating this process for all the 49 cells in the image. So once again, we look at some of the key contributions that have been made in this field. So if you look at YOLO, that was the first model, which is you only look once. Then the main contribution was to come up with these grid-based region proposals as opposed to the more expensive region proposals used in two-stage detectors. Then SST, with a single shot detector, came up with the idea that instead of only making predictions from the last layer of your convolutional neural network, you should use all the intermediate representations that are there in your network to make the predictions. And the idea there was that if you make predictions from all the layers, then you'll be able to detect both small objects as well as big objects. And then finally, RetinaNet took this idea further, and they said that we'll propose an entire feature pyramid. So we'll generate a pyramid of features and we'll make predictions from every layer of this pyramid, right? So these are the main ideas which have been proposed in one-stage detectors. Of course, there are hundreds of object detection models out there, both in the two-stage as well as the one-stage paradigm. But these are the main ideas that have been proposed, right? And this field has significantly progressed in terms of object detection performance on natural images. So now, having given a quick summary of what object detection methods look like, now I want to come back to our goal, which is to evaluate whether these models are sufficient for detecting objects in scientific plots, right? So let's try to see what happens there. So for this, we used a data set called Plot QA, which has bar plots, line plots, and dot plots. And this data contains over 220,000 scientific plots across different categories. And it is also, if you look at these axis labels, right, then they are all sourced from real world data. So this is, for example, race of students in a particular university. And then this is number of tourists that visit a particular place or a country in different years and all that. And this is sourced from various data sources like World Bank and international data sources. Right? So it has very realistic plots to begin with. Now, if you come to the evaluation matrix that I had explained earlier, so in object detection, you consider a box to be correct. So I would consider the red box to be correct if the intersection of this box with the true box divided by the union of the two boxes is greater than 0.5, right? That is what is the standard used for object detection over natural images. But as I explained earlier, this is not good enough for scientific plots, while it may be good enough for natural images. So we are going to use much stricter evaluation. We are going to evaluate these methods at much higher IOUs. So if you use an IOU of 75, then this is what a predicted box looks like for it to be marked as correct. But if I were to use an IOU of 0.9, then it should almost completely overlap with the true ground box, right? So as you increase the threshold at which you will mark a predicted box as correct, the evaluation becomes tougher and tougher. And this kind of tough evaluation is actually needed for scientific plots because you need very accurate localization of the visual elements in scientific plots. Okay, so let's start with the evaluation. So when we evaluated these models at a map of 0.5, which is a very relaxed evaluation criteria, similar to one used in normal object detection, these models seem to give very high accuracy, right? So their precision was close to 90%, which means that they were able to detect 90% of the objects in the plot accurately, right? But if you look at it at 0.5, what does the situation look like? Even this red box, which is having a very bad overlap with the green box, as far as accurately reading the data captured by the green box goes, it would still be marked as correct, and this is clearly not acceptable. Now, if we increase it to 0.75, the accuracy drops. In fact, it drops by quite a lot of points for the single stage detectors like single stage detector. And it also drops for the two-stage detectors by a considerable margin. And if I make the evaluation even more strict and realistic, as is actually required in scientific plots, where I'm going to mark the predicted box as correct only if it has a 90% overlap with the ground truth box, then the accuracy drops significantly. So whatever good accuracies you are seeing of around 90% at a threshold of 0.5, they all drop to 30%. And in particular, some of the one-stage detectors, they actually give only single-digit accuracy, right? So this shows that existing object detection networks, while suitable for object detection over natural images, are still not very suitable for object detection over scientific plots. And this, of course, goes back to some of the initial challenges that we had listed, which is the different sizes and aspect ratios of scientific plot objects. Right? Then we zoomed into this further. And in a scientific plot, you see objects of different types like bar plots, dot lines, legend labels, legend previews, plot title, and so on. And what we observed is that the lowest accuracy is actually seen for dot lines and for plot titles, which are very long. So a plot title is typically very long. It might even span 2 lines. So these are the objects which are detected with the lowest accuracy. Of course, across the board, the accuracy is low. It's not something to be proud of. But at least for these two cases, the accuracy was abysmally low. And if you do a qualitative analysis, so okay, at least here it seems that of all the models that we tried, RetinaNet and Mask RCNN seem to be doing the best across all the different models. Now, if you do a qualitative analysis, we see several problems. So this is the output of, this is a plot which was given, and these are the objects that were detected by the method SST. And as you can observe, it has actually missed one of the bars completely. For the other bar, it has a very poor overlap with the actual bar. And it has also not accurately detected the title. It has missed the first character of the title. If you look at YOLO, then again, you see a very poor localization in the sense that the predicted over box has is either longer or wider than the actual box. And also it misses a few detections in some cases. Similarly, if you look at RetinaNet, then you have a box which has been completely missed, and also a smaller box here for 2014, which has been missed. For Fast RCNN, it gets confused between the grid lines at the back and the bar graphs. So it detects multiple boxes within a bar graph, which is completely unacceptable because it will completely mess up the downstream values that are detected from these blocks. And also the longer titles are something that it is not being able to detect accurately. And faster RCNN does a very over-enthusiastic job of detecting multiple boxes where only one box should have been detected. And at the same time, the overlap with the ground box is not very good for this model. And similar problems are seen in mask RCNN also, right? So in summary, what we observe is that these methods are not good for detecting longer textual objects like titles of x-axis, y-axis, and the plot titles. They're also not good for very short objects like this one here. For example, this is getting missed here. And they don't work very well at higher IOU settings like this box here, which is acceptable in natural images, but from the point of view of reading the value of this bar graph, this is not acceptable. Right? The good things is that the feature pyramid network works very well. And the ROI align method, which does a better approximation of the features, also works well. Right? So, okay, how much time do you have?
Maybe a couple of minutes. Couple of minutes.
Hello?
Yeah, a couple of more minutes.
Okay. Okay. So then I'll just skip the second part. As I said, I won't have time to do it. I'll just go to the conclusions. So if you look at all the existing models, right, these are the existing models that we had evaluated. And this is an interesting plot where you have the accuracy on the x-axis and the inference time, right? That is how expensive it is to run these models. How much time do they take for processing every image? So ideally, we want models which lie here. That means they have a very high accuracy and a very low latency or a very low inference time, right? So all the existing models that we evaluated actually were low both in accuracy and also had a very high inference time. And based on our observations, we proposed a hybrid model first, which improves on the accuracy as well as is in the medium latency time in the sense that it is able to process the images faster. However, this is still not enough. The ideal region, as I said, is something here. And that's what we did in our subsequent work, where we proposed a very fast and efficient model. And that model was eventually able to achieve the required goal. I'll just skip over all these slides. And was able to give an accuracy of around 93%. And the inference time was also very low, which was around 23%, right? So the main takeaway from this talk is that existing models for object detection are not good at detecting objects in scientific plots. There are certain innovations required. In particular, the first innovation that we did was to combine some of the best ideas from existing models. And that's how we were able to push the accuracy to around 77% while having a reasonable inference time. But that was also not sufficient. Hence, we proposed this new model, which is shown in this diagram here. And this model was able to achieve a much higher accuracy of greater than 90% while having a very, very small inference time. And so that's the main conclusion from this talk.
Okay, thanks, Mitesh. Several of the questions are much more generic in nature. Maybe you can look at them later and answer. But one or two questions, maybe we're also running out of time. Why do we have to use CNN for doing such plot detections? Is that the only method available?
No, so CNNs have been very successful. So what you need to do in any kind of image classification or image detection is to be able to construct good features from the given image. And convolutional neural networks have been shown across multiple domains, like be it satellite images or natural images or even scientific plots. They are very good at extracting good features from the given image. That's why CNNs make sense in this kind of an application.
Okay, and maybe the remaining questions you can also look at it in the text and type your answers. Is somebody's asking, is this available in GitHub or something? The code?
Yes, the code is available in GitHub.
Okay, and do you use the same model for both text as well as the plots, the bars and
Yes,
lines
it's a
itself?
single it's a single model which does both the detections.
Okay, I think a few other questions. Maybe you can look at it in the chat box and you can respond to it when you get time.
Sure. I'll do.
So with that, I thank Mitesh for excellent presentation. I know you had to rush through the later part of your slides, but yeah, hopefully we'll have another chance to listen to you sometime in the future.
Yeah.
Thanks, Mitesh.